Mr. True. Almost in unison. All right, today we're going to be taking a look at induction proofs and hopefully give out some bonus points because you all watched the videos and got some understanding of this content last night. There are going to be, at least how I teach induction proofs, there's going to be 5 steps for induction proofs. We are going to be given a statement. And today we're only going to be looking at 2 examples, and they're both going to be partial sum formulas. When you're doing induction proofs for a partial sum formula, this is a sub 1, a sub 2, a sub 3, a sub k. This is a sum of k terms, or n terms, it will be k in a minute, of n terms, and we have like, you don't really have to add 1 and 3 and 5 and 7 and, you know, lot of, all these numbers. You can just go, hey, how many numbers you're adding? Just take the number of terms you're adding and square it. When you have a first a sub 1 term is 1 and you have a constant difference of 2, so this is a type of arithmetic sequence. If you want to do a partial sum of an arithmetic sequence that has a first term of 1 and a common difference of 2, this formula of just n squared will give you that partial sum. Now we were introduced to a partial sum formula. S sub n is equal to n over 2 times a sub 1 plus a sub n, but which is what you want. This is a partial sum formula that works for all arithmetic sequences. But we have a specific arithmetic sequence where the first term is 1, a sub 1 is 1, d is 2, and if it happens to be that very specific arithmetic sequence, here's an equation that lets you speed up the process of finding a partial sum. And I'm telling you it works all the time. Well, if you're going to prove that it works all the time, it's going to have to be, without a shadow of a doubt, this thing works no matter if there's 1, 3, or 5 terms. So I'm going to switch gears. Actually, I'm going to teach this a little bit differently than I just did last period. And I'm giving you this formula and saying, hey, this always works. Well, you might go, I want to make sure it works. So let's try it for s sub 1, when I'm only adding 1 term. If I write a subscript of 1, what am I saying n is? 1. So whether I write s sub 1 or whether I write n is equal to 1, it's the same thing. We got 1 term on the left, and that is equal to, well, this formula says when I'm doing 1 plus 3 plus 5 plus 7 plus dot, 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 up to 2n minus 1, this is the general term of this specific arithmetic sequence, that's equal to the number of terms squared. So 1 squared, well, yeah, 1 equals 1. Boom. S sub 1 is shown true. Okay, well, if this partial sum formula works for 1 term, let's see if it works for 2. Let's try s sub 2, where, of course, that means n is equal to 2. So let's grab 2 terms on the left. We got a 1 plus 3. Let's recognize that when I write s sub 2, I'm saying that n is equal to 2. So when n is equal to 2, does adding 1 plus 3, our 2 terms on the left, equal the number of terms squared? Well, we got 1 plus 3 is 4. 2 squared is 4. Boom. Therefore, s sub 2 is shown true. Okay, well, maybe you're really bored and you want to try it now with 3 terms. So let's look at s sub 3, where n is equal to 3. I don't care which, you don't have to write both of these, but let's look at s sub 3. That's 3 terms on the left, so 1 plus 3 plus 5. The right-hand side says, hey, just take the number of terms and square it. So let's try it. 3, n is 3 terms, 3 squared. We got 1 plus 3 is 4, plus 5 is 9, and 3 squared is indeed equal to 9. So s sub 3 is shown, oof, that's ugly, true. Now, I'm using the word shown. I haven't proven anything. I've just demonstrated or given an example that this partial sum formula works when there's one term on the left, two terms on the left, and three terms on the left. When we do a proof in mathematics, it's not like a science proof. You know, we're not taking overwhelming evidence, just evidence to state that some conjecture or hypothesis that we have is true. If this statement works 1,000,000 times and fails once, it is not true. It fails. When you're given a theorem or formula in mathematics and you're given here's Pythagorean theorem, right? That has to work no matter what values you plug in for a right triangle. This equation has to work, this partial sum formula has to work for any number of terms on the left-hand side. So just showing that it works a few times is by no means a proof. That's where the idea of an induction proof comes in. So when we do an induction proof, we're going to show that S sub 1 is true. I've arguably already done that, so I'm just going to erase part of this. We're then going to say, okay, I was given this formula, it worked once, so I'm going to assume it's true all the time. And the word assume is very important. These proofs, all proofs in mathematics are very, very structured concepts and processes that you have to walk through. If you're taking an IB exam and you leave off the word assume, you're going to lose that. It's either a method point or a reasoning point, and you may very well not be graded past that. It's that big of a deal. You are assuming. Now, why is it S sub k and not S sub n? Because this formula is written in terms of n. Kind of the same, I'm going to repeat the same thing that I said when we did trig proofs. When I said prove this identity true, your proof did not start with the full identity. We had to start with just the left-hand side or the right-hand side and create the other side of that identity or equation. You cannot use the statement you're trying to prove true in your proof. Like if I tell you to define a dog, you cannot use the word dog in the definition of a dog. It has to, you have to go around it. So this is arguably a formality. We're going to assume S sub k is true. We're just going to write the exact same formula, but instead of n, write k's. That's going to differentiate the work of our proof from the equation we're trying to actually prove true. We cannot write or use the equation that we're trying to prove true in its own proof. That doesn't make any sense. So it ends up being a lot of writing, but it is a formality that you must do. After we assume something true, this is something that I add into my teaching to make clear where the end of this process is. Like when we're doing, when we did all those algebraic expressions involving trig, and we were doing all that simplification, you're like, how do I know when to stop simplifying? This is going to be the end zone or the goal. Write out, I'm going to prove S sub k plus 1 is true. And the IE basically means like, I'm going to write out what it means, like as an example. Write out S sub k by substitution. This is not a proof. It's just going to give you an end zone, like a goal to try and reach. It's just strict substitution. Everywhere that our S sub k formula has a variable of k, we're going to remove that, and in its place substitute in k plus 1. And this is what this is either going to be, this line is either going to be where our induction proof starts or where our induction proof ends. When we do an induction proof tomorrow about divisibility, the proof is going to start with the S sub k plus 1 statement. With our examples today where we're doing induction proofs about partial sums, this is going to be the last line of our proof. I'm saying lots of things, but it may not make sense until you see the process. Go through the proof, and somewhere in your proof, you have to use the statement that you assumed to be true. That has to be in your proof somewhere. In today's examples, it'll be the first line. And with divisibility proofs, it'll be somewhere else. It'll be in the middle somewhere. Today, when we're at the end of our examples, when we're at the end of our proofs and we create this S sub k plus 1 expression and we know we're done, then we're going to write as our last statement. You need to basically memorize what this says on a higher level IB exam. This is the last point. You have to write this to get the last point. S sub k plus 1 is proven true, assuming that S sub k is true, and therefore by the principles of mathematical induction, S sub n is true. Use mathematical induction to prove S sub n is that this statement is true, that 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 is indeed equal to this shortcut formula of n squared. Okay, step 1. Does it work at all? Does it work for when n equals 1? Yes. So step 1 is done. Step number 2. We're going to assume S sub k is true. So we're going to assume, you cannot use another word as far as I'm concerned, and you cannot leave that word out. We're going to assume S sub k is true. And whether you write IE or not, that's just a habit of mine. IE, or like, for example, I'm just going to write this down again, but with a k. 1 plus 3, so if I miswrite this, help me out. 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 is equal to k squared. Now, our book does not state this in the proof, but arguably you should. Right now we're doing strictly these induction proofs on partial sum formulas, which is a direct relationship to sequences, right? And the domain of a sequence is positive integers. This is a sub 1, this is a sub 2, this is a sub 3, this is a sub n. And n is an element of positive integers. You would see this on an IB exam. So I'm kind of adding a little bit to my notes that are on, that you watched last night. Well, I just introduced a new variable. N is out, k is in. So I have to match this idea of defining k as an element of positive integers. Step number 3. This is my little extra line that I include just to give us a goal. When do we know when we're done? What is it we're trying to prove? We're going to prove S sub k plus 1 is true. I.e., now all I'm going to do is write this exact same equation, only everywhere there's a k, I'm going to do substitution. I'm going to substitute in k plus 1. So 1 plus 3 plus 5 plus dot 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 plus 2 times k plus 1 minus 1 is equal to k plus 1 squared. Now, through the rest of this, there's going to be a little bit of a variation from the video notes you took, with the goal that hopefully I make this stuff make more sense. Okay? So here's our proof. I'll go back to, I'll keep it in black so it's easier to read on the camera. So here's our proof. I know I'm starting the word, I know I'm starting the proof because I wrote the word prove. Now, in all induction proofs, you must include the statement that you've assumed to be true. With partial sum questions, that will always be the first line for our problems. So we're going to start with what we assume to be true. 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 is equal to k squared by assumption. We assume that to be true. Now, let's emphasize this for a second. The left-hand side is the sum of how many terms? K terms. So this is the sum of k terms. And that's the formula, a shortcut formula for adding k terms. I'm going to take that, and it's a lot of repetitive writing, I'm sorry, but you have to do it. 1 plus 3 plus 5 plus dot 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 plus 2k minus 1. I'm going to leave some room. On the right-hand side, I have a k squared. This is a sub 1, a sub 2, a sub 3, a sub k, which one more time, just for emphasis, means that that expression is a sum of k terms. This is the shortcut formula for adding that many terms in this specific sequence. Well, I erased this, but we showed the formula worked for one term, then we showed the formula worked for 2, then we showed the formula worked for 3, and if we were doing a bunch of examples, we would show that it worked for 4. So we're going to algebraically extend this partial sum to not k terms, but k plus 1. So I'm going to take s sub k, and I'm going to add the a sub k plus 1 term to both sides. This is not a strict substitution. I'm literally adding one more term. So if this is the sum of 7 terms, I'm going to add the 8th. If this is the sum of 100 terms, I'm going to add the 101st term. But we're doing this not, with arithmetic, but with algebra. So this is a sub k, right? Because it's s sub k. And since this is s sub k plus 1, this is the what term? This is the a sub k plus 1 term. This is your general term. This is a sub n. This is your general term. This is a sub k. I'm going to add, I'm just going to substitute in k plus 1. I'm going to add the a sub k plus 1 term to both sides. I'm going to add 2, not times k, but times k plus 1. And then, of course, I have another minus 1, right? I'm going to add that to both sides. Now, I'm only doing this for notes in terms of all this subscript writing to make you understand what's going on, hopefully. But just for hopefully clarity, hopefully for emphasis, Ethan, if this black is a sum of k terms, if this black expression is s sub k, and I added one more term, then this is all s sub what? Correct. Which means all of this stuff on the right-hand side has to be what? Correct. And when I took my equation that I was assuming to be true, and I said assume s sub k is true, and then I said, hey, I'm going to prove that s sub k plus 1 is true. I'm going to prove that when you add k plus 1 terms, that the answer is k plus 1 squared. So does k squared, the sum of k terms, plus the k plus 1 term, plus 2 times k plus 1 minus 1, does all of this simplify to be k plus 1 squared? And if it does, you've completed your proof. And if it doesn't, then this formula fails somewhere with some number of terms. I don't care where, you know, if it's 100 or 1,000,000 terms, but somewhere this fails. So let's simplify this out. Let's distribute the 2 and add like terms. So we got k squared plus 2 times k is 2k. 2 times 1 is 2 minus 1. So now we got k squared plus 2k. 2 minus 1 is 1. Is this factorable? Is k squared plus 2k plus 1 factorable? Are there factors of 1 that add to 2? Yeah, it's 1 and 1. So this becomes k plus 1 times k plus 1, which happens to be what? K plus 1 squared, which is a match. I took the formula for S sub k and just substituted in the expression of k plus 1 and got k plus 1 squared. That gave me the goal line. That gave me the end of my proof. This is what we want to get to. The sum of k plus 1 terms is k plus 1 squared. The proof started with the partial sum of k terms, and we just added one more term to both sides. We didn't do substitution, we just added another term. We recognize that the sum of k terms plus the k plus 1 term is the sum of k plus 1 terms, and we were able to simplify that right-hand side to be an exact match. Now, once the proof is done, what do we write? This statement. You can't change it. So, bam! That's not the end. S sub k plus 1 is proven true, assuming S sub k is true. Therefore, by the principles of mathematical induction, you can just abbreviate that to PMI, S sub n, so we're back to n, S sub n is true. Woo! I love this stuff. Use mathematical induction to prove that one plus 3 plus 3 squared plus ... 3 to the n minus 1 is equal to 3 to the n minus 1 over 2. Now, every time you see a little S sub n, that doesn't always mean partial sum with induction proofs, but we are doing just partial sums today. So what's step 1 to prove that this equation works? Cole.
Prove that S sub 1 is true.
Prove it works at least once. And use the simplest number you possibly can, which is n equals 1. So for step 1, for n equals 1, or you can write S sub 1, either one I'm going to accept. We've got one term on the left. 1 is equal to 3 to the first minus 1 over 2. That's 1 is equal to 3 minus 1 is 2. And 2 divided by 2 is, of course, equal to 1. So therefore, S sub 1 is shown true. And what's up?
What happens if that was not true?
Stop. It's false. Yep. Step number 2. Assume S sub k is true. And I'm going to write this horizontal since I'm a little bit shy on space here. 1 plus 3 squared plus ... plus 3 to the k minus 1 is equal to 3 to the k minus 1 over 2. If that negative 1 comes up into the exponent, I'm just being silly, dumb, made a mistake, whatever you want to call it. Let me know. Of course, k is an element of positive integers. just like n was an element of positive integers. What's the next line? Substitute in k plus 1 and say that you're going to prove s of k plus 1 is true, which is to say that we've got 1 plus 3 squared plus dot 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 plus, now let me go ahead and include this one more time. What is this 3 to the k minus 1? What term is that? A sub n or a sub k now? Yep. And we're substituting in k plus 1, so our a sub k plus 1 term, and I'm not going to simplify, I'm just going to write 3 to the k plus 1 minus 1 is equal to, take out the k and substitute in k plus 1, 3 to the k plus 1 minus 1 over 2. This is the end goal. I want to be able to add k plus 1 terms and show that the answer is 3 to the k plus 1 minus 1 over 2 using the formula for k terms, using the formula that we're assuming to be true. Because, you know, it worked once. All right, so we're going to start the proof, which starts with all partial sum formulas that we'll see in this class, starts with what you're assuming to be true. So I'm just going to copy this down. I'm sorry, you have to. 1 plus 3 plus 3 squared plus dot 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 plus 3 to the k minus 1 is equal to 3 to the k minus 1 over 2. Get down there out of that exponent. Now I'm going to take that partial sum of k terms and I'm going to add an additional term to both sides, like I did before. So I'm going to copy this again. 1 plus 3 squared plus dot 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 plus 3 to the k minus 1. This time I'm going to leave some room to add the a sub k plus 1 term to both sides. This is not substitution. I'm actually going to add a term to both sides of this partial sum formula. We're going to add that a sub k plus 1 term to both sides. Remember, this is s sub k. This is the sum of k terms. We're going to add the k plus 1 term to the left by just taking out k and plugging in k plus 1. That's the a sub k plus 1 term, adding to the left and adding to the right. Making sure I didn't write something silly. All right, so s sub k plus the a sub k plus 1 term. Does that simplify? Can I make the right hand simplify to 3 to the k plus 1 minus 1 over 2? If I can, I've completed the proof and shown that this works no matter how many terms are in there. So let's see if we can't do that. How many terms, I've used red a lot already, sorry. How many terms are in our final answer that we need to construct? That's one big fraction bar. How many terms is this? One. How many terms do we have on the right-hand side right now in our proof? Two. We need to make those 2 terms into 1. So basically, we just need to add these fractions and hope that we get this as an answer. Okay, so, I mean, let's clean this up a little bit. We know 1 minus 1 is what? 0. So now we have 3 to the k minus 1 over 2 plus 3 to the k over 1. What do you need to add fractions? Common denominator. I'm not giving a point for that. So we're going to multiply the numerator and denominator by 2 to get that common denominator, right? So now that we have this common denominator of 2, we've got 3 to the k minus 1, that's a little bit close, minus 1, 2 times plus 2 times 3 to the k all over 2. Does this numerator have any like terms? Well, if you're just thinking like simple algebra, you might think the answer is no. But yeah, what are the like terms? Between 3 to the k minus 2 times 3 to the k, what are our like terms?
1 times 3 to the k and 2 times 3 to the k.
Yeah, the two terms that have the base of 3 and the exponent of k. What's the coefficient of this 3 to the k? 1. We did this back in like chapter 2 when we were factoring quadratics and some of the bases were numbers. The base is not always a variable. Sometimes it can be a number. This 3 to the k has a coefficient of 1. And this 3 to the k has a coefficient of 2. Well, what if you're doing 1x plus 2x? It would be 3x. You just add the coefficients. So 1 times 3 to the k plus 2 times 3 to the k is 3. You add the red numbers, you get 1 plus 2 is 3. So we have 3. I'll keep it in red. 1 plus 2 is 3, just to emphasize it. So we have a new coefficient of 3 times 3 to the k minus 1 over 2. Okay, we're getting close, but we need a 3 to the k plus 1. Well, we have a multiplication of two bases that are the same. When you multiply like bases, what do you do to the exponents? You add them. What's the exponent? See, I haven't used blue in a while. What exponent is on this 3? A 1. On the camera, that blue and black probably looks the same. Then we have 3 to the first times 3 to the k. Multiply those bases, you get what? 3 to the k plus 1. So our final line here, we have 3 to the k plus 1 minus 1 over 2, which happens to be an exact match. Bam! Not done. Okay, we have to write the statement. S sub k plus 1 is proven true, assuming S sub k is true. Therefore, 3 dots, therefore, by principles of mathematical induction, I'm sorry, I'm standing in front of you guys, ladies over there. By PMI, by principles of mathematical induction, S sub n is true. Bam! Go do your homework. And then, of course, don't do the division problems.